Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light, where we have been looking at the work of John Tyndall, his lectures on light. In my last lecture, I talked about chapter 22 in A Student's Guide Through the Great Physics Text. We went through the introduction, which talked about the biography of John Tyndall, and we also talked about some of his introductory comments on the speed of light, and he's relating it to the speed of waves traveling through an elastic medium. So just to remind you, the velocity of sound depends on the elasticity, or the bulk modulus, to use a technical term, of the medium, the stiffness of the medium, divided by the density of the medium under a square root. And so if you were to make a medium stiffer like steel, sound would travel more quickly. If you were to make it less dense, it would also travel more quickly. In any case, one of the main points he makes is that light, because of its great velocity, whatever medium that it's traveling through must either be a very stiff material or a very rare material. That's what he's talking about on page 258 and 259. Then what Tyndall goes on to talk about is how light is a transverse wave as opposed to a longitudinal wave. So let me remind you what he's mentioning here. So if you think about, I'm going to draw some axes here. Let's draw an x-axis and a y-axis. And if we imagine that we have a string stretched along the z-axis, I'll make this string brown, we might imagine that if we shake it up and down from the end right here, so if we were to hold on to the end and shake it up and down in this direction, what would happen is that you would have waves traveling down the string. Those are transverse waves. And the point that Tyndall was trying to make is that that would be called a vertically or y-directed polarization wave. Now, just to kind of give you a sense of how this might be filtered or blocked, you might imagine if we were to take this string and pass it through a cardboard sheet. So imagine we have a cardboard sheet like this, and we were to cut a slot in it like this, and we were to pass this string through that slot. If we had the wave shaking up and down, then it would easily make it through that slit. On the other hand, if we were to shake it back and forth, so if we were to shake our hand along the x-axis so that this string would shake back and forth in this way, that would be horizontally polarized, and then that would be blocked and it would not make it through the filter or this cardboard sheet with a slot cut in it. So I'm only saying these things because it's going to play into our discussion of polarizing filters later on. And the point is that for transverse waves, you can have two independent polarizations which can be blocked by slits oriented in a certain way. Now, before I go on to his continued discussion, I want to mention one other thing. I've mentioned that if you have a string, it supports transverse waves. And if you have, let's say, air, that supports longitudinal or compressional waves. But you might imagine there might be some materials that sustain both kinds of waves, transverse waves and longitudinal waves. And as an example of this, imagine that we had a block of jello. So I'm going to draw a block of jello right here. And this goes a little bit beyond what Tyndall is talking about right here. But imagine we have jello. Now, let's suppose you wanted to make this jello wiggle. Well, one thing that you could do is put a plate on the end, like a sheet of metal or something on the end. And if you were to take this sheet of metal and shake it up and down like this, that would cause transverse waves to travel through the jello. You would have kind of wiggles going up and down through the jello, right? So as it kind of wiggles up and down, I'm trying to draw it kind of shearing as it wiggles. See if I can draw this like this. So you might imagine these wiggles traveling through the jello. That would be an example of a vertically polarized or a y-polarized transverse waves. You could also shake this plate back and forth along the x-axis, and in that case, you would have x-directed, again, this is x-directed and this is y-directed, or you'd have, again, transverse waves that are polarized along the x-axis. I'm not going to try to superimpose those wiggles on top of it because that would only confuse the drawing, but this jello supports transverse waves. But notice also that if you were to take your hand and let's suppose you were to slap this sheet, you were to slap the jello, swinging your hand forward and slap it, well, in that case, you could have compressional waves traveling through the jello in this direction. That would be a longitudinal wave if you slap the jello like that. So the point that I'm trying to make is that jello sustains both longitudinal waves, or compressional waves, and transverse waves. And that is because jello is I guess, a compressible material, and it's also, in some sense, a solid, where the parts of it are kind of bound to other parts of it, okay? If you have something like water, like liquid water, that supports longitudinal waves. If you compress water, you get compressional waves traveling through it. But because the parts of the water aren't bound to each other tightly, water does not support does not support transverse waves. You can shake if you were to immerse a plate in water and shake it back and forth, you could make the water move a little bit back and forth, but that wouldn't sustain these waves traveling through the water. So water, because of its non-solidity, cannot support transverse waves in the way that a solid like jello can support transverse waves. Why am I bringing this up? Well, this is going to prove to be a puzzle for the theory of light that people like Tyndall and others are going to be advocating. They're going to advocate that light is a transverse wave. But keep in mind that this implies that light is traveling through some medium that in some sense behaves as a solid. Because after all, only a solid like jello can support transverse waves. So if you believe that there's some medium that's undergoing these vibrations, and those vibrations are transverse, you must somehow believe that the medium through which light travels is a solid. That's something that Albert Michelson is going to bring up in the late 1890s as in a sense, maybe an insurmountable difficulty of this transverse wave theory of light. Okay, so I mean, we're looking a little bit ahead right now, but I thought it's worthwhile bringing this up. Okay, now if we go on page 259, what Tyndall is going to continue talking about is how light, when it's traveling through certain kinds of media like calcite or Iceland spar, it is divided into two beams. This is birefringence that he's talking about, and that is something that he talks about in the second to last paragraph on page 259, and then he points this out on the following page in figure 22.2, where there he shows a light source, and that light source produces unpolarized light. That is, it has both vertical and horizontal transverse polarizations to it. That is focused by a lens E, and then it passes through a piece of Iceland spar at point P, and then that light beam is divided into two beams, an ordinary and an extraordinary beam. And what he points out here is that by understanding light as having two distinct polarizations, and also the Iceland spar having two different bond strengths in different orientation, we're talking about the architecture of the crystal, that gives rise to different light speeds and hence birefringence. So he's going to be developing this idea. He says here specifically that the ordinary ray, that is the one labeled O in his diagram, the ordinary ray obeys Snell's law, the law of refraction, with a refractive index n to be 1.654. So that's why it's called the ordinary ray, because it obeys Snell's law. But there's also this extraordinary ray. So some of you saw this in the laboratory when you looked at birefringence, passing light through a crystal. And this one bends light with an, it bends light with an index of refraction that varies between 1.483, he mentions, that's a lower bound, and the upper bound is 1.654. So it's going to, 654. He said it depends on the precise orientation of the crystal, but the extraordinary beam bends with in a way that it would imply a refractive index between these two numbers. And perhaps more importantly than it bends the light is that the incident and the refracted extraordinary rays do not lie in the same plane. What do we mean by that? Well, if we had this sheet of Iceland spar, like this, I'm imagining a block of it, and imagine you have a light ray coming in like this. Well, remember we can draw a plane of incidence. So if I were to draw the point here and sort of a plane like this, in which this incident ray lies, ordinarily the refracted beam lies in the same plane. So the ordinary ray the refracted beam would lie in the same plane. But the extraordinary beam, as he mentions, does not actually lie in the same plane. It lies out of that plane, okay? So that's why it is referred to as an extraordinary beam, because it doesn't seem to obey these ordinary laws of refraction that we came across first when we studied the works of Newton. You might remember in his optics, in his 5 axioms, one of the axioms is that the incident beam and the refracted beam lie in the same plane. That's not the case with this extraordinary beam in that Tyndall is talking about here in his lectures on light.